guys, well, welcome to week 4, I guess we're on now. Recitation. Not as many in here today as last week, but that's all right. Maybe they'll come later in the week. I am recording this to try to get another recording out there. My recording from last week had video issues halfway through the recording, so I'm going to try again. Except I forgot my pen for my little tablet writing thing, so I don't know how good my writing on the screen is going to be this time. To start off with, are there any questions on anything that anybody wants to ask?
Is project 3 the same as last time?
It's the same except for part 1.
Okay.
So we gave you a little bit more structure by giving you part 1 to kind of get your brain kind of going towards what the program needs to do. So part 1 seems pretty helpful. Just to kind of arrange everything in your brain. Yeah. What do you mean?
Is it the same as last time?
As last semester? Oh. Yeah, same as I assume you meant same as last semester. Yeah.
Are we going to go over the first set was talked about last?
We are not going to do that. We're going to go over longest prefix match and syntax analysis, a little bit of CFGs, and then maybe, if we have time, a little bit on project 3. The first and follow sets, my first one of those will start on Thursday for first and follows. Those are, kind of conceptually tough. So, but I wanted to get through the other stuff for your homework and whatnot for those that may still be having a little bit of struggles with them. Anything else? Cool. So as you guys have talked about, the purpose of the Lexer, the purpose of the get token is basically to take your source code, take bytes, and turn it into tokens. And tokens are specified by regular expressions versus the next step you guys have talked about, the context-free grammars that are used to specify syntax. Why? Does anybody know why? Why might we use regular expressions? Why not just use context-free grammar for tokens as well for reading stuff in? The CFGs, do they describe more complex? Is there more complexity that CFGs can describe?
Like recursion?
Yeah, they have recursion built into them. So they have a higher level of complexity. The nice part with regular expressions is they can be used much faster. And so when you're reading stuff in just to turn it into tokens, we want something that's super fast. And so we use regular expressions because while they can't do everything of the CFGs, this reduced capability that they have makes up for it in processing, ability to process stuff faster. So just kind of warm back up on regular expressions. Take a look at what's up here. Can anybody come up with a word that fits this regular expression, or words actually? It's several.
A-A-L.
A-A-L?
A-A.
Just what?
A-A-L.
A-A-L. Yeah, A-A-L words. A-E-L.
A-O-N.
Addition.
Addition's the one that I put in there specifically. Had another one that was pretty long too, pretty long word that somebody else found in last class, but once your brain starts going, thinking. A-O-N. Is that a word? Horrible. It's probably. Words with friends, I'm very bad at that. So another one somebody said last class was animal. A, yeah, N-I-M-A-L.
Heading.
What?
Heading.
Edit?
L.
Yeah.
ABC. Yeah. AEEICD. But it doesn't have a C. Doesn't have C. Yeah.
It's close. And it doesn't sound like it ends in A-L, E-L, or O-N. I don't know. It's just fun. Okay, so longest prefix match. We use this when we're faced with a string of characters and we want to know which regular expressions apply given our list of regular expressions. So the process that I use for this is similar to what he did in class. I just kind of stuck it into slides instead of doing it by hand. In theory, to minimize errors. Still finding errors every time I go through this, so we'll be debugging it a little bit together, but hopefully it's a little cleaner now. I've gone through it a couple times. So the string that's passed in is positivity is in your mind, and we're going to use these rules, these rules to kind of figure out which ones apply. So for which one of these are currently, as with the P as input, which ones are potentials? Which ones could somewhere possibly be a match down the line? R1? All of them? Yeah, doesn't start with a vowel, so R1, R3, R4. Now, what about letter? Is letter a potential? Or is letter a match? Letter's a match. So, letter's a match for one character. And we have R1, R3, and R4, and then since R2 and vowel aren't available anymore, they're marked through up there. Okay, so now we move on to the O. Does the O change anything? Do we still have R1, R3, R4, or do we lose one of them?
R1 is a match. So it's R.
Is it a match, or is it
It's
still a potential?
Potential.
Yeah.
R4 is potential. Oh, we lose R3.
R3 can be letter.
Oh.
Letter
I
repeating
confused
like
everything, yeah.
infinitely, right? So yeah, they're still the same. Yeah, with no match on this one. So nothing matches 2 exactly. So we go to positivity, or we go to the S now. Does anything change?
R4 is a match.
Yeah, R4 is no longer a match because we have letter, vowel, vowel, and S is not in our set for vowels. So we lose R4, so it's marked out up there now, and we still don't have any exact match. So right now, if we were to be at the end of the string, our only match would be letter 1, and we'd go back to the P and start over, but fortunately we have a lot of string left. So, all right, now that we're on the I, does anything change? I heard it. Did I hear 1 is a match? R1 is a match? Yeah. R1 is a match, and R3? The screen. The screen went out. The screen went out over here.
I think it's just off from there.
Yeah. Well, everything reset. I'm wondering if the power. I wonder if we had a power fluctuation or something. Back? Oh, good. Then I won't turn it off. All right, we're back. So we've got our R1 is a match, and R3 is still there. R1 is no longer potential. There's our first typo of the game. Yeah, R1 can't be potential anymore. I should have taken it off that one. So now we move on to the T. What?
R3 becomes a potential.
Yeah, and no matches. Go to the I. Oh, you get to cheat on this one. R3.
Yeah, R3 is still potential.
Yeah, still potential. Now, we get to the TY. So R3 becomes
Potential.
match.
Oh, yeah.
R3 is a match for 10. It's still a potential though. You guys can't see me pointing at my screen over here, can you? On my laptop, I don't think that's helpful. So yeah, it's still a potential, isn't it? Because we could go back to letter. There could be another TY. We know is because we can analyze it really fast that there's not. But the point is that this is algorithmic, right? So there could still be a TY on the screen, so we assume that there will be. So we keep going. We look at the I this, we go all the way to the end. And now there's nothing. And so we go back and we get the R310 is the longest match. And that goes back to there. We reset everything back to there. And now I'm resetting my screen. Every rule is available again because we had our longest match. And we're going to match on it again. And so we start with the I's. We start with the I. And I is a vowel, so which ones are potentials now? Yeah, which two are, or which ones are potentials? Yeah, so R1 through R4 are potentials, and then what are our matches? Or single match or no match? Yeah, letter and vowel. Yeah, that one kind of right. Comma 1, right? So letter, comma 1, vowel, comma 1.
And if there's a conflict, then any
If there's a conflict, what?
between letter and vowel. So we
If we ended right there and we had both of them where they're equal to 1, typically what we'll do is by order of the rules, I think is what the homework was. So you look back at whatever one's first on the list, and it's kind of natural if there's a tie between them. No cheating. So we have I and then S, so now what do we have? R2 and R3, we lose. We lose R1 because of the vowel and lose R4 because of the vowel. So R2 and R3. Oh, we forgot. We get a match on R2 here, right? R2 only needs to be these two to get a match. So we've got a 2-link match. So now we go to the I. Alright, you guys get a freebie. So we get R2, R3. Are there any matches? No. Yeah, so let's go on to the end. What about now? What do we have? R3? Yeah, and the match on R2. R2 is still a potential at this point. I mean, we know looking forward that on the next one it won't be anymore, but it's still a potential as of right now. So now we go to the Y. What are potentials with the Y? R3. Yeah, and R2's gone, right? We can't have a Y is not considered a vowel. So just R3, and so far our best one is this R2 with 4. But we're going to check it out just to be thorough and go all the way to the end. We don't see a TY, so there's no potentials left. Our longest one is this R24. And so we take that one, and now we go on to the Y. keep kind of going through the same process. So, freebie, maybe. Clicker works. Work. So we match on the single letter, and we still have available R1 and R4, and I thought I fixed all these typos. Oh, it magically is correct now. So you have R1, R3, and R4. Now that we go to we're on the O, which ones are our potentials? R1, R3, and R4. Oh, boo. And then we don't have any matches yet. What now? R1 falls out, or it's still good, it's still a potential. It's still good. I think I made a mistake. Yep. I did. God, it's so hard to do. It's hard to get these right. Yeah, so R1 is valid, despite what my screen is going to say, because the U matches. This is a really good case of where I should probably get partial credit, because I think I'm now thinking that's going to mess up the rest of my slides. So you get to hear, if R1 was still in there, it would match as well. We'd have a tie. Right? And then it would loop back around, and yeah, it messes up the rest of my slides. So what we're going to end up with is wrong. R4, if we just arbitrarily throw out R1, then we're good. then this is correct, but can't make up the rules as we go like I just did. So I just want to be clear, it's wrong. R1 should be in there, and what should happen is, since as we move on to the next one, if we will notice, I'll just go to the end, but that R1 matched here too, and since they would have been together, it would have been R1, 8 instead of because this wouldn't have been there at all, and this would be replaced with R1, 8 because it would have kept going where we had to end the first one. Wait. No, I'm lying. Oh, I'm lying. All right. So R4, this should be R1, so it should be R1, R4. It should be both of them. And then we go on. So it should be both. Because R1 is first in the list, we should have matched on that one. That's actually much easier to fix in my slides. So we should have gotten a match. This should have been R1, 4 as well. I'm not going to fix all of them. But since R1 was higher in the list, this should have been R1 instead of R4. And then everything else holds. We couldn't, just like with here, R1 and R4 can't go on any further because they're only 4 characters. That's the most they could ever match. So it couldn't be 8, so I lied again. Yeah, that's correct. So R1, R4, and then because R3 is still a potential until we get to the very end. And so R3 was still there, but it never matches, just like before. So we keep going. So yeah, this one is now there, and we're going to just pretend that it's still there on the subsequent slides. So you end up with you end up with R1, 4, and then R1, 4 again as two separate tokens. And that was 70 slides, guys. We've been through 70 slides already today. Each one of those changes had to be a separate slide, which is part of why the mistakes are just so easy for me to do, at least. My mistakes are not an excuse on your exam, though, or your homework. So, all right. I want to just kind of make this point. You take each one of these tokens. If we ran get token on it, each time we run get token, it's going to, it'll return an enum value. So in this case for R1, which is wrong, so it returns that, but and then the length 10 matches. So those are all the global variables that are set that we used on project 2, just to kind of reiterate how the get token was working with these guys. So the is-in would be returned on this one, token length 4, your, which apparently, I think you guys get the drift. I will fix the slides. So, for lexical analysis, we focus on the tokens. What are they and what do they look like? We define them using regular expressions. So we get returned back to like the ID, the num, and all the other tokens that we can bring in, and they're maybe in some kind of list or some kind of data structure. And then for syntax analysis, we're looking more at whether the order that we brought them in, whether that's valid. And so we're more concerned with the actual order, and that's what we use the CFGs, is to investigate the order and find valid orders. So as we kind of talked about, we define valid syntax by using context-free grammars instead of regular expressions. We talked about this earlier, but we'll go ahead and reiterate why. Why don't we use regular expressions for the syntax? No recursion, right. So we have no way to specify, to build really long grammar, or really long strings. So it's a subtle difference. But in regular expressions, we have the star. We have the star operator, which allows us to build infinite strings. But the regular expression itself is fixed. It can only be a fixed length, a finite length. What context-free grammars allow us to do through recursion is build that actual expression to be as long as we want it to be. And so that additional power is what allows us to count and gain the ability to count things that are in the string by matching stuff up. Yeah, so an example, we've seen parentheses, I thought I'd do something slightly different, would be, the curly braces, you can have a bunch of them, but they have to match. If you have an opening one, you have to have a closing one. And so we would, CFGs aren't able to do that, but there's just no way to do it to an infinite number with a regular expression. We could say our language only has 10, max nested parentheses, then we could do a regular expression for that. But not infinite. Not when we don't know. And we want it to be infinite. I'm sure that there are aspects of Windows 10 that has more than 10, curly braces embedded within, if statements or whatever. Hopefully the code's better than that. But you never know. Yeah, so the CFGs, the expressions themselves can be infinite, and that's really the difference. So you guys talked about in class leftmost versus rightmost expansion. It has to do with when you're looking, which terminal, which non-terminal do you expand? Do you do you start with the ones on the left or do you start with the ones on the right? And it sounds easy when you say it like that, but it's always stranger when you're in there in the heat of the moment trying to do it. So we want to create the string A, B, C, D, A, B, C, F using a leftmost derivation. This should be fun. Since I don't have my pad today. That doesn't look that fast, is it? No, it's totally real. Alright, so if we're going to create a tree for this, what do we start with? So, we wanted, what was it? We want to be able to build the string A, B, C, D, F. Do another. Alright. It's readable. So what do we start with? If we're going to build the tree, we kind of want to see the tree. What do we start with first?
Symbol S.
Yeah, with the S. Cross your fingers, this works. Hey, look at that. So we start with S, and then we're wanting to build this string over here, so which one of S's?
Brackets.
The brackets, exactly. So we got, that's going to be too big, but we'll make it work. Right? And then where do we go?
Let's go with X1.
Yep. Now what is?
Extends to ABC.
Yes. That sounds good. And then we will go over to Y. Yeah. Which one? Yeah. I don't know if my handwriting looks much better with my tablet. Hold on. So then we go with X goes to what? Yep. Are we done? Yeah. So we'll print out, we got that guy will print, and then ABC, and then D, and then ABC, and then F. Final with a bracket. Cool. That's right. All right. Oh, let's see if I can. Will it remember? That's going to be close. Perfect. All right, so looking at this just from a definition standpoint, what are the non-terminals? Which are the non-terminals? S, X, and Y. Yep. And then, so what does that mean? What are the terminals then? Yep. Yep. F, D, epsilon, ABC, and then each bracket are the terminals. What's that? Yeah.
But doesn't that depend on the grammar? It can be
Well,
included.
in this, but it is in this grammar. So yes, it does depend on the grammar, but it is in this grammar.
But I think it depends on the alphabet, right? Whether we include it into.
Not on the alphabet.
Because, I don't know. Sigma? It depends on sigma, right?
No, it's an operator. It's just like it was in a regular expression. It still is just a stand-in for no string. So if we wanted to go we have that xy there, we wanted x, we could have x go to epsilon at any point. And all that is just saying, it's kind of a placeholder for saying, so that we know we can come back to this rule and we can skip having any x, so there's no value there. It's just kind of, but when we're looking at a grammar, it's just a placeholder. So there would be no epsilon in the language. If you passed in an epsilon, string, or you wanted us to create an epsilon string, it wouldn't be. My recollection is, and I don't think he's probably talked about it since then, he won't have something like that. He won't torture you guys like that. He might do it on regular expressions, but he won't do it on the context-free grammars.
Okay.
So anytime a non-terminal has a rule with those two epsilons, that would be that's not like
Well, the epsilon would be a terminal. Yeah.
I mean,
Yeah.
that's like something special non-terminal.
I would, well, yeah. It's different on the program. So the program, when you guys have the program, will be different. The way you define epsilon is by basically having an or with nothing there. And that'll make more sense if you've looked over the specifications for Project 3, that would make a little bit more sense. But basically, you don't have the or signs for the Project 3. The equivalent is just having something be defining a non-terminal multiple times is the equivalent to or. And so you just have a non-terminal that's just terminated with nothing there, with the hashtag on the end, and that says that non-terminal definition's ended, since nothing was defined for it, it's your effective epsilon. All right. So now let's do this guy. After how awesome you guys did on the last one, this shouldn't be too bad. All right, what do we start with? S. That's the easy one. Got it. Now what?
S bracket.
Bracket. Bracket, S, bracket. Now what?
Again, S bracket.
Yeah, perfect. Like how my handwriting got bigger now that I'm like, oh, this one's not going to take us long. Now what?
XY.
XY is right. Gotta get smaller so I can fit.
X tends to 1 side.
Yes, exactly.
Y tends to
And then Y?
F.
F. I can't write on this screen and listen to you guys at the same time. It's not possible. Brain just explodes. So we've got that guy, nothing, right? So I mean, we could even write it as that. It's nothing. And then we've got an F, and then this guy, and then this guy. See how it's just kind of a placeholder there for us, the epsilon? Cool. All right, last one. D, E, F. And we start with sigma?
S.
S. Yeah?
S tends to XY.
To XY? Perfect. Now what?
X.
X goes to where? Epsilon. Exactly. What does Y do?
XY. DXY.
DXY. X goes to epsilon.
No, Y goes to DXY.
DXY, right? Everybody agree? I see that? X goes to epsilon again.
Y goes to
y goes to f. So we got all these, we got the empties, and then we got a D that sneaks in there, and another empty, and then a D that sneaks in, another empty, and then an F. End up with DDF. That's perfect. So, is this CFG that we have here, is it ambiguous?
Yes. Why? Because you can have for the same string, you can have two different parse trees.
Yeah, two different parse trees
Yep.
that are both. There's one important aspect to that. Not just the same parse tree.
That both have the same string.
Same string, same parse tree. Anybody can help? It's the last part. For
Leftmost and rightmost.
Yes, exactly. It has to be. Yeah, it has to be all left. Both parse trees have to be leftmost, or both parse trees have to be rightmost. So you have to create both parse trees using. I would just use leftmost expansion, but that has to be. That's the third thing. It has to be the same for it to provably be ambiguous. If you're taking 355, you definitely run into that. So, does anybody want me to do the two parse trees, or can everybody kind of see? You want to see? Okay. Let's do. What is something simple, short that we can do that would
do expose to XY. You go expose to XY and then F1 and F, and then go expose to SY and then Y goes to XY and then F1 and F.
yeah, you're kind of hitting on that probably will work because you're hitting on where the ambiguity is, right? The ambiguity in here has to do with this XY and then this repeated XY, and that's going to give us multiple paths to kind of go down. So I think you're on the right track there with it. I know, for example, the first example that we did, the ABC, D, ABC, F, that we could actually do it two leftmost expansions with that one. I did that. That was my example I did when I was putting this together. So you basically, let's see, if we were doing that one, we could, well, we absolutely need these, so that would be the same. And then, not necessarily. So we go to XY, and then so here's where we could do it different. I don't recall that we had that epsilon there, but then we just come over here and we do XY again, and now it's different. Now it's a different parse tree, right? But we're going to end up with the same ABC, D, ABC, F. So, but we were able to go a different parse tree. And the whole key here, or the whole thing, was that these two were the same.
Is that always the case? I mean, that's pretty straightforward. You see XY, F, XY, Y. But is there a case where
If
you don't have matching, it's still be?
Well, yeah, if they're not, you have to get them to line up, right? You have to get them to kind of line up in the same way, too. It's not just that they're the same non-terminals, but it's that they're the same non-terminals, and I can finagle it to get them in the same kind of, to get them to line up in the same way that it does without it. So that's part of it, but not always. I mean, there are other ways to have ambiguous trees, because as these get bigger, right, as this gets a lot bigger, you can have ones that have some of the same expressions within them that could cause ambiguity. So there's a ton of different ways to do it. The trick is finding the parse tree, that is leftmost expanded that matches, and you find two different ones. And it takes some trial and error. It takes some brute force. And then, yeah, I mean, the first thing you probably want saw two that were repeated, the first thing you probably want to do is explore that, especially on an exam or something, when you know that there's typically going to be an answer to something. So from a kind of game theory test-taking standpoint, then sure. But never guaranteed in real life. I mean, they try to make them so that they don't have ambiguity in them. As makes, I think, more sense kind of after you get first and follow sets. The whole descent parser wouldn't work when you have ambiguity. That's going to sound horrible. All right. So who's read, at least glance through Project 3, the Project 3 description? Who's done with it? Anybody done with Project 3 yet? I mean, we'll keep saying this. I'm sure he's already said it, but start early. Start early. Start early. You guys can absolutely have Part 1 finished this week without any more lectures. If we didn't have any more lectures, you have all the tools you need to finish Part 1. And it will give you some of the foundations for Part 2 and Part 3 just from a programming perspective. That's why I was saying it's really nice of him to do that, to add that in there, although it's an extra step for you guys, but it's something where you can start on a simpler problem, start thinking through some of the issues that you're going to have and that need to be solved. So you have to do it in C or C++. The key here is you can do it in C++, which is great if you're more comfortable with it. And I think C++ is a little easier. You can do it however you want. I know people that go through and try to do all the programs in C. It's kind of what you're more comfortable with, what you're good with. I came from a Java background, so I definitely hopped on C++ as soon as I could get away with it. It's just, even if it was mostly, I think, just for the string object. Because C strings are just such a nightmare. But hopefully Adam doesn't listen to these presentations and hear me talk about how C strings are a total nightmare. But I'd say it if forced to again. So you can use the previous Git token that we used in Project 2. I would do it. That's what I would do. That's what I did. You'll have to change it. It's made for a different set of regular expressions. These are different. It's going to have, we have what, 4 tokens or something that this can have, so that's all it's going to have to return. And I don't know, I took it and played with the actual code from Git token this morning, and granted it's easier for me, been programming for a long time and whatnot, but I knocked that out pretty fast, just changing it up. And then you know that works. You don't have to worry about knowing if your Git char's right and all this different stuff. It just kind of, that part's already built in there. You've already got line numbers, and I mean all this other nice stuff just built in there for you. I think I did that for the same thing for the next one too, but I can't remember now. So, up to you if you want to modify it or not. You can always write your own. So, grammar description. Kind of have this multi-level of grammar, right? So this grammar is describing the grammars that'll be in the input file. And so it's taking, okay, these are the valid things that it can do. We have 4 tokens. We have ID, hash, double hash, and arrow. The ID, just like on our other stuff, has to start with letter, and then can be as many letters / digits as you want to put in there. And the key here is that this is what's describing what's going to be in your input files. And then your input files can be a whole other separate, kind of independent, what they can do, can't do, all that. And hopefully that'll come across with some of the examples. So this is the grammar description, the full grammar description for the project. You have your S, and then you have a non-terminal list. So the first line in the file is over here on the example side. This is kind of that first line, and then you hit the hashtag. As we'll talk about later, lines don't matter. It doesn't care about lines. It cares about its hashtag delimited. So if it has a hash, then it's going on to whatever the next thing is. So it looks in. This was nice. This was really nice of Adam or whoever originally did this to include this in here. It makes it much more difficult to have to go through and figure out which ones are non-terminals, but you've got all your non-terminals listed right here. So your non-terminal list comes down and you can have an ID list and it's ended by hash. And then
hash is more like end of line, and double
Yes.
hash is end of file.
yes,
Oh,
exactly. So the actual new line character is irrelevant. And I have if we get to it, I have an example. So yeah, then if you look at, so then the next thing is the rule list. This is the rule list. All these guys right here make up the list of different rules. A rule list is prepended by a rule, which is down here, and then is attached to the rest of the rule list. Or it's just a single rule. A whole rule list could be just one rule, and that's what the other rule is there. And then a rule is made up of an ID, so this is the ID, an arrow, which is this guy, and then it's made up of the right-hand side and ended with a hash. So this is the right-hand side, and this is the hash that ends it. And then right-hand side is, look at that. Kind of useful. It's an ID list. So we just have another list of IDs, and that's our right-hand side, terminated by the hash. All right, so here's a different example. I was trying to be nicer on this one and give the variable names to be a little bit more prompting than the example that was that's in the project description. So looking at this grammar, what are the non-terminals? This isn't a trick question.
NT1, NT2, and NT3.
Yeah, exactly. All right, what are the terminals?
Amp, pipe, ID, semicolon.
Yeah, exactly. Amp, pipe, ID, semicolon are the terminals, and the non-terminals we already said, NT1, NT2, NT3, and they're listed at the top. So here's crazy style. This is where I was talking about. This is just as valid as the last one. It's just we're not worried about where the new lines are. They could be anywhere. All right. So for part one, you're going to have. So there are 3 different parts. For part 1, a 0 is passed in as an argument, and that'll tell your program, okay, go run part 1. So when a 0 is passed in as an argument, that means it's going to execute your code for part 1. The part 1 is basically coming up with a summary. So you're outputting a summary of all the information that's in the file, kind of non-terminals, terminals, etc. So the first line of this summary is going to list just all the non-terminals delimited by a space. So a bunch of different ways to kind of do that, but they're listed in order that they're encountered. This is kind of important. So I was actually just thinking, hey, I could take the first line from the input file and just basically print that back out, and that'd be my list of non-terminals. Except this is specifically meant to mess with that. So it's the order that it could be up top is totally independent of the order that it appears down here. And so when you have the rule list, that's what governs what order you're going to print these out in, is based on the rule list. And I will guarantee you there is a test case in there that tests that. There's just no way that there's not. And then after last non-terminal line, so after this non-terminal line, the first line of the thing, this you will actually end with a new line character. This is just the output that's required. This is output versus we were talking about the input before. All right. So the remaining lines are dedicated to your terminals and seeing how often they show up. So the output style is a terminal followed by a colon and then a space, and then how many rules in which it appears. So this is different. If it appears 4 times in the same rule, that still only counts as once. And then at the end of each one, it's a new line. So here's an example. Okay, this is similar to the one we had before, except I added these 2 guys on the end. So the output, oh, look at my animation failed me. You guys getting free answers. Alright, so NT1, NT2, NT3, really good. AMP2, but like I said before, that is not counting this one. That is actually counting this one down here. So that's 2, and then pipe, all the other ones are pretty self-explanatory, right? So the number of times that AMP2, the number of rules that AMP2 shows up in. This is not the number of times that AMP2 shows up, it's the number of rules that it shows up in. AMP shows up in NT2. Oh! Actually, I'm going to have to ask Adam, I don't know the answer. If anybody knows what I just realized. So, NT2 is still the same rule. So I'm actually thinking that it should be 1. It should be 1 and not 2. But I'm going to have to verify that. Just to be sure. But I'm pretty sure that's what he's going to want. I'm pretty sure. There. So that is a mistake. Yeah, and then all the other ones are pretty self-explanatory. We'll call that a mistake at this point, and I'll send out some kind of clarification to the email list once I get it from him. Alright, last example. Yeah. Alright, given this input, what? AMP is 1 given this input, yeah. So there's 2 things going on. The AMP is on the line, but this is considered in a file. We hit this double hash, and we quit reading. So you hit the double hash, you're done. So at the point you're done, AMP is 1. Although we found out from the last slide before last, talking through it, that AMP probably would have been 1 there. But you get the point. The point is that this is valid. There's nothing that says you can't have junk following it. So this is where it ends. It ends right there where the double hash is. And I went over. I'm sorry, guys. That's it.